Code review and testing exist to find security weaknesses before software is deployed, when fixes are cheapest and impact is lowest. Once code is running in production, weaknesses turn into incidents, emergency patches, and operational disruption rather than planned improvement. From a security perspective, software flaws are not just bugs, they are latent attack paths waiting for the right conditions. Reviewing and testing code shifts security left, embedding risk reduction into development rather than bolting it on afterward. The goal is not perfection, but early visibility into weaknesses that would be far more expensive to address after release. Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Code review focuses on examining source code to understand logic, data handling, and how security controls are implemented. A reviewer looks for how inputs are validated, how authentication and authorization decisions are made, and how sensitive data is processed and stored. This kind of review reveals intent, showing what the developer meant to do rather than just what the software happens to do at runtime. It can uncover flawed assumptions, missing checks, and logic errors that automated tools may miss entirely. Because source code expresses design choices directly, code review is one of the most powerful ways to identify security risk early. Peer review is a particularly effective form of code review because it brings multiple perspectives to design and implementation decisions. Another developer can often spot unsafe patterns, edge cases, or overcomplicated logic that the original author overlooked. Peer review also reinforces shared understanding of secure coding practices across a team, turning security into a collective responsibility rather than a specialist concern. Many serious security flaws originate not from malice or ignorance, but from reasonable decisions made under time pressure that were never questioned. Peer review provides that questioning in a constructive way. When done consistently, it raises the baseline quality of both code and security awareness. Static testing analyzes code without executing it, scanning source or compiled artifacts to flag risky constructs and known weakness patterns. These tools look for issues such as unsanitized inputs, unsafe function calls, hard-coded secrets, and flawed error handling. Static testing excels at scale because it can analyze large code bases quickly and apply consistent rules across projects. It is particularly useful for identifying classes of issues that recur across many components. However, static analysis cannot fully understand business logic or intent, which means its findings require interpretation. Static testing is most valuable when used as an early warning system rather than a definitive verdict. Dynamic testing complements static analysis by running software and observing its behavior under test conditions. Instead of examining what the code looks like, dynamic testing examines what the application actually does when it receives inputs and executes logic. This approach can reveal runtime issues such as injection vulnerabilities, authentication bypasses, and error handling flaws that only appear when the application is exercised. Dynamic testing is especially useful for finding issues that emerge from interactions between components rather than from a single line of code. The limitation is that dynamic testing only sees what is exercised, so untested paths may remain unexplored. Together, static and dynamic testing provide different lenses on the same risk. Security unit tests are another layer that validates expected behavior at a granular level, focusing on input handling, authorization checks, and error paths. These tests assert that security-relevant logic behaves correctly when given both valid and invalid inputs. For example, a unit test may confirm that unauthorized users cannot access restricted functions, or that malformed input is rejected safely. Security unit tests are valuable because they codify security expectations directly into the development process. When a future change breaks a security assumption, the test fails immediately, alerting developers before release. This approach turns security requirements into executable checks rather than informal guidelines. Dependency analysis addresses a different category of risk by identifying known vulnerable libraries and components used by applications. Modern software rarely consists solely of custom code. It depends heavily on third-party libraries and frameworks. Vulnerabilities in these dependencies can expose applications even when custom code is well written. Dependency analysis tools compare used versions against vulnerability databases to highlight known issues. This visibility allows teams to prioritize upgrades or mitigations before vulnerabilities are exploited in the wild. Managing dependencies is an ongoing process, not a one-time check, because new vulnerabilities are discovered continuously. Test environments play a critical role in the effectiveness of both static and dynamic testing, because results are only meaningful if conditions resemble production closely enough. Differences in configuration, authentication flows, or integrated services can hide or create vulnerabilities that do not exist elsewhere. If test environments are overly simplified, dynamic testing may miss issues related to scale, permissions, or integration. At the same time, test environments should be isolated to avoid unintended impact on real users or data. Balancing realism and safety is essential. Well-designed test environments support reliable security conclusions without introducing operational risk. Test data management is another often overlooked concern because using real sensitive information in testing creates unnecessary exposure. Test data should be representative enough to exercise logic paths, but it should not contain actual personal, financial, or regulated data. Poor data handling during testing can result in data leaks through logs, test tools, or shared environments. Masking, synthetic data generation, and controlled access help reduce this risk. From a governance perspective, test data should be treated as a security asset with clear handling rules. Secure testing practices include not only finding flaws, but avoiding the creation of new ones. Prioritizing findings from code review and testing requires considering exploitability, impact, and asset sensitivity rather than raw finding counts. Not every issue flagged by a tool represents meaningful risk, and not every low-level issue can be ignored safely. Exploitability asks whether an attacker can realistically trigger the issue, while impact considers what would happen if they did. Asset sensitivity adds context about the importance of the affected system or data. Without prioritization, teams can become overwhelmed and focus on cosmetic fixes instead of real risk reduction. Effective prioritization directs limited remediation effort toward the issues that matter most. False positives are an inherent challenge in both static and dynamic testing because tools err on the side of caution. A reported issue may be mitigated by surrounding logic, environmental constraints, or compensating controls that the tool cannot see. Triage is therefore essential to confirm whether a finding represents real risk. This process requires collaboration between developers and security reviewers to interpret results accurately. Excessive false positives can erode trust in testing tools and cause teams to ignore important signals. Managing false positives thoughtfully preserves the credibility and usefulness of security testing. Secure coding standards provide the expectations that guide both review and testing, defining how validation, authentication, authorization, and logging should be implemented. Standards create a shared language for what good looks like, reducing ambiguity during review and remediation. They also allow testing tools to be tuned to the organization's expectations rather than generic rules. When standards are clear and accessible, developers can design with security in mind rather than discovering requirements late. Secure coding standards turn individual findings into lessons that improve future code. They are a force multiplier for review and testing efforts. Reporting is where review and testing results are translated into actionable guidance, tying issues to specific code locations, recommended fixes, and verification steps. Good reporting explains not just what is wrong, but why it matters and how to address it. Developers need enough detail to fix issues efficiently without guessing or reinterpreting findings. Security teams need traceability to track remediation and verify closure. Poor reporting turns useful analysis into friction, slowing down improvement. Clear, structured reporting ensures that review and testing outputs lead directly to better software. Code review and static and dynamic testing build security into software before release, when change is still manageable. Review reveals intent and logic flaws, while testing exposes risky constructs and runtime behavior. Unit tests and dependency analysis extend coverage into areas that manual review alone cannot reach. Effective environments, safe test data, and disciplined prioritization make results meaningful rather than overwhelming. Secure coding standards and clear reporting ensure that lessons are learned and applied consistently. When these practices are integrated into development, security becomes part of how software is built, not a last-minute obstacle to delivery. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.